So today in class, what we're going over is a new topic, okay? We've been going over for the past couple of days how to do rate of change problems, okay? Now, the thing about all the rate of change problems we've done so far is they've all been rate of change problems involving just one thing that's changing, okay? So, we only had one variable that was changing throughout and that was fine, okay? However, do a lot of systems use just one variable?
No.
No, they have like multiple variables, right? So like for example, if I'm looking at how a volume changes, okay? So let's say I'm doing like a tank of water, okay? And I want the volume of, let's say it was a conical tank of water. If I want like, if I'm draining the tank, how does the cone of water change as I drain the water out of it? Both the radius of the cone and the height of the cone are changing, right?
Yeah.
That's two different variables, not one. Uh-oh, we got a problem there, right? The derivatives we've worked with so far have only been working with just one variable. We want to know how to deal with it when we have two or more, okay? And that's what we're going to cover today. We're going to talk about something called implicit differentiation. Okay? So, we started off with, when we solved problems before, we were doing them with what's called explicit, okay? So explicit versus implicit, okay? Explicit differentiation, you're basically just doing the derivative of one variable only. And you're also explicitly told what you're taking the derivative with respect to, okay? So like in f of x, for example, we know we're taking the derivative with respect to x, okay? The position equations are x of t, we're taking the derivative with respect to time, okay? It's explicitly stated what we're taking the derivative of, okay? With implicit, it's not quite so straightforward. We can do it for more than one variable. And we also have to determine what the dominant variable is, what variable we're taking the derivative with respect to. Okay? So must determine the dominant variable. Okay? So let's take a look at examples of each of these so you can see the difference of what I'm talking about here. Okay? So an explicit example we've seen before. There are things like f of x equals 3x squared minus 2x plus 1. What would the derivative of that be? 6x minus 2, right? Easy peasy mac and cheesy, okay? Another example of explicit might be something like y equals 4x squared over 3x minus 2, okay? And that we could take the derivative of, right? We would say y prime then is equal to, what rule would I use?
Quotient rule.
Quotient rule. Low-D high minus high-D low.
Just 3.
Over low squared. Okay, and we're good, right?
Right.
Any problems with that? We can do that because these are all explicit. They're already written, basically, all these functions are written as functions of x, and it's fairly easy to determine then how to take the derivative. We're taking, all the derivatives are with respect to x, so we just apply the various rules and we get our answers. Okay, super easy at this point. Implicit examples are a bit different, okay? Okay? These are for things that aren't written in the terms of x. Okay? What might be something that's not written in terms of x? Can anyone think of like an equation that we've used before that has multiple variables in it?
Oh, like yesterday for the expanding of the blood vessel. Does that have multiple?
Finding the
You say
slope of
multiple
soil.
equations or variables?
Like x, f of
multiple
x,
variables.
f of x plus h.
Okay, not quite like that, because that's still just a matter of h there is going to 0, so that's not what I mean. I'm thinking more of like an object. So for example, what would the equation of a circle look like? Anybody remember that from pre-calc?
Minus k
Oh, it's
squared.
it's the ace.
X minus r, x squared minus
X
whatever.
a squared plus y a squared
Okay, so
or y b squared.
you're on the right track. That's actually, by what you're saying, it sounds more like an ellipse there. But, you know, a circle, remember circles are like x squared plus y squared equals r squared, right?
No.
Okay, so an implicit example might be like a circle, okay? X squared plus y squared equals 16. That's a circle, right? We had other things like hyperbolas or other weird shapes. This guy right here on the board, if I wanted to graph that shape right there, that has the equation y cubed plus y squared minus 5y minus x squared equals negative 4. And just so for the notes in the video, the thing I'm talking about looks somewhat like that there, actually. That's a bad drawing. Let's do it better. Looks almost like a medicine ball or one of those things, okay? I don't know what you would, sack, I don't know, okay? But a shape like that there, okay? These, how difficult is it to, I could try to rewrite them explicitly in terms of x's, but that's going to make a lot of work for me, right? And it's also not going to be 100% correct, especially with something like this one right here. I could rewrite it, but I'm going to have y equals plus or minus the square root of 16 minus x squared. Well, that doesn't help me out very much. I got two formulas there, a plus and a minus. This one right here, if I try to write it in terms of x, I get something that's really nasty, right? In fact, could I write this one down here where it's y equals things in x easily? No, because I've got 1, 2, 3 y's, and they're all different powers and things like that. Okay? Could you write it in terms of x? I'm sure if I gave you a CRC manual and a ton of time, you might be able to do it.
Wait, but that's
Okay.
not a function, is it?
Well, it's not a function, but we don't need these. Remember, we're not talking about functions. We're talking about regular equations here. Okay? And there are plenty of equations that make graphs that we'll want to find tangent lines to. Okay? That aren't necessarily functions. So, with these, we have to do what's called implicit differentiation on them. Okay? So let's see how that's done. Okay? Those are examples of things that have to be implicitly done. Okay? So, how implicit differentiation works. Okay? So, we'll do our first one. X squared minus y squared, or plus y squared equals 16. That circle. Okay? Now, here's our example problem. Okay? Basically, what you want to do first, a lot of times in these equations, is determine what you're going to make your dominant variable. Okay? So, basically, pick a dominant variable. Okay? 90% of the time, it's given to you. Because you're told to either find a tangent line in terms of y equals mx plus b, or y minus 1, etc. In which case, x is going to be the dominant variable. Okay? Or you're told to find a derivative with respect to something. Okay? Now, you can change things up here. You can pick actually technically any variable to be the dominant one. Okay? But again, like 90% of the time, it's given to you. When in doubt, just be safe and always pick x to be the dominant variable. Okay? Or if it's a problem involving, like a physics problem, pick time to be the dominant variable. Okay? So, when in doubt, or not told, pick x. Okay? Alright, so we're going to take the derivative of this thing with respect to x. Okay? That means the non-dominant variables okay? In this case, they don't become constants like we saw before. Instead, non-dominant variables become chain rules. Okay? And you'll see what I mean here in a second, okay? So, going through, taking the derivative of y squared, of x squared plus y squared equals 16 with respect to x. What's the derivative of x? 2x, right? That's easy enough, okay? We would get 2x. I'm going to save the y here for a second. We're going to do the derivatives of both sides now because we've got both sides of the equation. What's the derivative of 16? 0. Okay? That's easy enough. Now when we hit y squared, okay, we're going to treat it like a chain rule. So I can think of this as being the derivative of, or basically of y, in parentheses raised to the second power. So it becomes what if I do chain rule? 2y times whatever the derivative of y is, okay, with respect to x. Now, we're not going to make it 0 here, but we don't necessarily know what it is. We're just calling it derivative of y with respect to x, right? So dy by dx. Okay? And hey, isn't that actually kind of what we're trying to figure out anyway? The change in y with respect to the change in x? Yeah, that's what the derivative is, right? So
just
now what are we going to do, you think?
solve for dy over dx.
Good, good. Very good. You're doing better than other people have so far at this. So yeah, 3. Now, solve for dy by dx. Okay? So we've got 2x plus 2y times dy by dx equals 0. We move the 2x's over, the 2x over. Divide by 2y. Okay? Or we get an answer minus x over y. Okay? So,
dy dx
dy by dx is equal to minus x over y. That means then, for my original, that's the derivative with respect to x of this original equation, okay? Which also means if I'm trying to use applications of the derivative on this thing, I know what equation I should use.
Hold on real quick.
Okay, yeah, certainly. Okay. Okay, so for example, had I wanted to find the slope of a tangent line, okay, to my circle, this equation tells me what the slope should be. Okay, I would plug in my point for x and my point for y and get my answer. We'll do that in a second, okay, with an actual problem. Okay, yeah.
Why is it equal to, how did it change to 0?
Oh,
Oh, derivative.
yes, the derivative, it was a 16
Yeah.
out there, and the derivative of 16 is 0.
Alright.
Because 16 is still a constant, there's no variable there.
You
Okay?
take the derivative of negative x over y.
Yeah, I can take the derivative of that. That'd be the
That
second
would be your
derivative.
answer.
Huh?
Or no, that would be your answer.
No. So this is my answer right here.
Okay.
This is what the derivative with respect to x was of the original function, or original equation, not function, it's a circle, okay, is minus x over y. Now, I could take the derivative of this, but that would be the second derivative, okay? So the slope of this thing would be the second derivative, okay? Alright, but does everyone see how that works? Okay, let's look at another example. Let's look at the weird cowbell, horseshoe-esque graph. I don't know what you want to call it, okay? It was another example. Get some practice here, okay? We've got y cubed plus y squared minus 5y minus x squared equals negative 4, okay? And what we want to do here is, again, we want to take the derivative of it, okay? With respect to x.
So
Now,
x is our dominant variable.
sorry?
X is always our dominant variable.
Generally speaking, unless otherwise stated, you're always doing this with respect to x or with respect to time, okay? I say time because again, the real world physics problems, it's times the Dowell's variable. Okay? So, someone go ahead and tell me, how would I, so I'm doing it with respect to x,
Would each y variable be its own chain rule?
it would be, okay? So what would it look like?
So,
3y plus,
So
No.
3y
or times dy.
squared times dy by dx, okay? Plus
plus 2y, dy dx,
2y times dy by dx
minus 5
minus 5
dy dx,
dy by dx, good. Minus
2x,
2x, because this is x, it's easy, equals
0.
0, okay? So that's how that thing comes out to be. Now, before I go any further, yeah, well, before we do that, just want to make one point here. Although y's, we treat them as chain rules, but look what really happens. Look how easy it really is.
Cancel.
You just do the regular old power rule to y, and just add on a dy by dx on the outside. Okay, that's really it. That's all you're really doing. Okay, so instead of confusing yourself by saying every y is a chain rule, which is what the book will tell you, instead just think, do the derivative normally, but just recognize it's not x, so add dy by dx on it. Add the derivative with respect to x to the end. Okay, and you're good. Now, as someone was saying before, my next step would be what?
Move x over.
Move x over and do what with the dy by dx's?
Factor.
Factor them out. Good. We'll go ahead and we'll do that. Factor out the dy by dx's. Equal to 2x. And then that means dy by dx is going to be what?
2x over 3y squared plus y.
Right.
2y minus 5.
2x all over 3y squared plus 2y minus 5. That's my dy by dx, okay? Now, this, what you might have been told from the beginning here is instead of just doing the derivative of this, let's say the problem was a little bit more involved. Let's say it was find the tangent line to y cubed plus y squared minus 5y minus x squared equals 4 at, what's the point? It's the point 1, negative 3, okay? What would I do?
Y
Well-
plus 3.
I would do, yep, coming down here at the bottom, okay? Because I want this. Our tangent line would be y plus 3 equals
that.
dy by dx evaluated at those points, okay? So evaluated at 1 and minus 3, okay?
Where'd you get the y plus 3?
Y minus y1 equals dy by dx times x minus x1, okay?
What are we finding the tangent line to?
The original function,
Sorry, what was the point?
the point we're using at, okay, original function, my original function, the point's 1, negative 3, okay? Okay, so, but it's dy by dx times x minus 1, okay? dy by dx, we need to figure out what that is. We just evaluate this thing at 1, negative 3. So it would be dy by dx at 1, negative 3 is 2 times 1 over 3 times negative 3 squared plus 2 times negative 3 minus 5. So 27 minus, what is that, 6? So, yes, 27 minus, 27 minus 11. What's that going to be?
25 minus 11.
27. 16. Okay? So it's 2 over 16. Okay? So 1/8. So it's 1/8. Okay? So this dy by dx down here, we would replace it with 1/8. So my tangent line is really y plus 3 equals 1/8 x minus 1. So, okay? So that's an application of how these things work. Okay? So now the weird horseshoey shape gets a tangent line. Okay, fine. Okay? Any questions how that works? Nope. Alright, let's look at another example. Okay?
Wait.
Oh, need me to go back?
Yeah, for a second.
Yep. Back down. Next example we're going to look at here is going to be one where things are a little bit more involved. Okay.
Wait, but why? So 1/8 is essentially the derivative.
Yeah. It's the derivative at 1 and -3. It's a change in y with respect to the change in x at that place. Okay?
Okay.
Which is what we're finding. And isn't that what slope is anyway? Isn't it rise over run? Change in y with respect to
1/8
x?
is the slope.
Huh?
1/8 would be the slope of the tangent.
Which is exactly what we figured out. Okay? And that's what we're doing here with implicit differentiation. Okay? Okay? Alright. Let's look at another two examples of this. Okay? So, kind of other examples where these things get a little bit trickier. Okay? Let's look at find dy by dx of x squared minus 3xy squared plus 2y cubed equals 4. Okay? Well, if we start this off the usual way, okay, what's the derivative of x squared?
2x.
2x, okay, minus, we'll hold off on that for 1 second. What's the derivative of 2y cubed?
6y squared dy dx.
dy by dx, good. And the derivative of 4 is?
0.
0. How will we treat 3x y squared?
6y dy dx.
Can we just take out the
Well, what would that be? We have an x and a y together now. That's two different things, right?
3,
The product
6y.
It's a product rule. Good, David. It's a product rule, okay? So, we do the derivative, we keep the first thing the same, so it will be minus 3x times the derivative of the second thing, which would be 2y dy by dx. Okay? And then we add to it, okay, derivative of the first thing, which is 3, because 3x is the first thing, times the second thing kept the same, y squared. Okay? And so that's what it comes out to be. And now we've got it to where we want it to be. It's just a matter of cleaning this thing all up. Okay? So 2x minus 6x, excuse me. 6xy dy by dx minus 3y squared plus 6y squared dy by dx equals 0.
Wait, where did that 3 times y squared come into the picture?
3 times y squared?
Yeah.
Again, we're treating this as a product rule. Okay? Product rule says keep the first one the same
Yes.
times derivative of the second one
Okay.
plus derivative of the first one times the second one kept the same. So the 3y squared comes from the second half of the product rule.
Okay.
3 is the derivative of 3x, and y squared stays as y squared.
But would it wouldn't be minus?
No, it's a product rule. Okay? Product rule is always plus. Notice how I put it in parentheses, and now I'm handling the minus sign. That was out in front. Okay? Yeah. Whenever you do that, yeah, definitely do what I just did there. Use the parentheses to keep track of the minus signs and things, okay?
that's fully cleaned up?
Not yet, no. Okay. Basically, it's fully cleaned up, by the way, and as far as simplification is concerned, you're done when you have this thing written as dy by dx equals stuff, okay? So we would have to keep working until we got to that method here. So the next step, I'm going to get everything that's not dy by dx over on the other side of the equation. This is minus 6xy dy by dx plus 6y squared dy by dx is equal to minus 2x plus 3y squared, okay? I could factor dy by dx out there, right? Okay? So if I did that, give myself a space here, I would have dy by dx times minus 6xy plus 6y squared equals minus 2x plus 3y squared. And to finish it all out, dy by dx is equal to minus 2x plus 3y squared all over minus 6xy plus 6y squared. And so that is the slope or the derivative of the original function with respect to x, okay? Note though, okay, so if this is a test or a quiz, I don't have to simplify that down. Actually, this doesn't simplify down. That's as easy as it gets, really. Okay, but even if it did have things I simplified, I wouldn't necessarily have to do that, but I do have to get this in the form of dy by dx equals, okay, before I'm done with my answer. Okay, so now I'm done. I don't have to go any further. Everyone see how that worked?
Yes.
Okay. Give you guys a second to copy down what's there. Okay. We can see this too, as well, with things involving all the different rules. So we could do a chain rule with this. We could do a quotient rule. We can do anything you want to. Okay. So if I looked at another example, okay. Let's say I wanted the derivative. I want dy by dx of the tangent of x over y, okay, equals 3, okay? Well, derivative of the tangent is what? Secant squared, excuse me. Thinking cotangent. Secant squared x over y times the derivative of whatever x over y is. Well, that's going to be a what rule? Quotient rule. So it's going to be low d high minus high times the derivative of low all over low squared. And what's 3 going to be? 0. Okay? And so now it's just a matter of cleaning that thing up. And that thing is rather nasty to clean up, but you could do so. Like, right now, we're not going to actually clean it up, but what you would do is you distribute the secant squared, okay? And then get rid of the y squared actually will go away. It will, because when we cross multiply it, we get rid of it, okay? And then from there, continue to clean things up, okay? So you could do it, it just takes a while, all right? But notice how the actual derivative went, okay? The process. So,
Even though you're asking about your dy dx, you're not going to make it right now?
well, no, not right this second. Just because we're running out of time in class, and also too, at this point, there's no calculus involved. We're done with the calculus by this point, okay? At this point, it's just cleaning something up, which you should know how to do from algebra 2, okay? Actually, you should know how to do that from algebra 1. So, you get the idea. Any questions on how this works, though? Okay. Tonight's homework is going to be a lot of implicit differentiation problems, just so you get used to this, because we're going to be using implicit differentiation to do much more complex related rate problems, which is what our goal is to do, okay? Just get off, obviously, this doesn't come up that much. There's just not that many things we care about that have x and y, but there are lots of systems that use implicit differentiation where it comes to real world examples, and that's what we're getting at. Okay, so this is to help you learn how to do that. Okay, any questions? All right, we're finished.